Welcome back. In this short segment, I'm entitling it Impedance Transformations. We're wanting to learn how to transform different interconnected structures of impedances, whether those start as a delta interconnection, and then we want to go to the Y, which the diagram here is showing the deltas in black and the Ys in blue, or whether we start with three impedances that are configured in a Y structure interconnection, and we want to transform those into something that looks equivalent between these three terminals, A, B, and C, in the delta configuration. In this material, you can find the equations in section 9.6 of the 10th edition of Nielsen and Rydell. Our goals then are, starting with this, we either have them in the black, the delta, or the Y, the blue, and we want to convert to the other interconnection structure. Right now we are labeling all six of those impedances as a unique subscript. The deltas are with A, B, and C, and you might notice that the Z sub A impedance is opposite the A vertex in the diagram or in the delta configuration. The B impedance is opposite the B terminal, and the C, Z sub C, is opposite the C terminal, whereas in the Y configuration, we are going ABC in correlation with 1, 2, 3, so that the Z1 impedance is touching the A terminal, the Z sub 2 impedance is touching the B terminal, and those Z1, Z2, and Z3 are connected at this mutual terminal of, let's say, a neutral terminal. We want to then determine if we have this delta configuration, Z sub A, Z sub B, and Z sub C, can we obtain a new configuration in the Y, the Z1, Z2, Z3? And we will start with the balanced impedances. We want to show or derive this formula in going from delta to Y. If we're starting with deltas, then we're having the ZA, ZB, and ZC already known, and we want to find Z sub 1, Z sub 2, and Z sub 3. I'm just showing you the Z sub 1 formula. The Z sub 2 and Z sub 3 formula will have the same structure, not the same exact formula. If we wanted to go from Y to delta, then we would have this different formula. We would be starting with Z sub 1, Z sub 2, and Z sub 3 and deriving what the Z sub A, Z sub B, and Z sub C are actually equal to. If you look at this, Z sub 1 is the Y impedance that touches the A terminal. If we go back and we look at that, and now look at the numerator of the right-hand side of that transformation, we now can see that Z sub B and Z sub C both touch the A terminal, and what's in the denominator is the sum of the three. If you wanted a strategy then, if these weren't labeled with Z's A, B, and C and Z1, 2, 3, you could say, oh, if I want the impedance that's sitting in the Z1 location, I take the two delta impedances that touch the same terminal, which are ZB and ZC, and divide by the sum of those three delta impedances. That's what we could sort of say if we had to memorize this particular transformation relationship. If we were going from Y to delta, it's just a little different, but not too much different. Now if you look at Z sub A in the delta, the impedance that's opposite to that, the terminal opposite to it, is the A terminal, and that A terminal touches Z sub 1 in the Y configuration, and that's the impedance that we actually divide into this pairwise, or this sum of pairwise products of Z1, Z2, and Z sub 3. That's sort of a way to think about where these formulas might be coming from if you had to memorize them. If we looked at the case where the 1, 2, and 3 and the ABC are all equal, if we call the Z deltas or the impedances in the delta configuration, if we label that as Z sub delta and we label the impedances that are in the Y configuration as Z sub Y, then these two formulas above, which you would really have six formulas, but three are for the delta to Y and three are for the Y to delta, they all end up giving you the same expression. If we look at what we obtain in going from delta to Y, if we start with the deltas, then we have a Z delta times a Z delta over a sum of all three of those Z delta impedances. And now we have then Z delta squared over 3Z delta. We can factor out a common Z delta between the numerator and the denominator. And we see, in fact, that the balanced Y impedance is a factor of 3 less than or smaller than the delta impedances. If we did the same process in going from Y to delta with this Y to delta unbalanced formula, now you replacing those unbalanced impedances with balanced values, we now have a pairwise product of ZYs that we sum up 3 different times. And downstairs we just have one such product. You see that we now could cancel one of those ZY factors in the numerator and denominator, and now we end up with just 3 Z sub Y, and in fact then Z sub delta is 3 times the size in value as our Y impedance. And that's, if you wanted to stop watching this video and you were worrying about this balanced transformation, you could simply keep track of this formula that relates the value of your delta impedances relative to the value of your Y impedance, and now you're finished. You just need to know that they differ in size by this factor of 3, and the delta impedances, which here in this schematic are somewhat larger than the Y impedances graphically, well, in reality, when you start computing these, they also will be bigger. The delta impedances are 3 times bigger than the Y impedances, and that's what we just derived. That's actually one of our goals. The second of our goals is to show that, but really once we've found the first goal, which are these relationships, we can already see what the balanced configuration will produce. Let's then look at deriving this relationship in going from a delta configuration to a Y for unbalanced impedances. If we go back and we look at the impedance between terminals, let's say AB between terminals BC and between terminals C and A, let's start with the impedance between A and B for both the delta interconnected structure and the Y interconnected structure. If we go back to the delta and we say, what's the impedance seen between A and B in the delta configuration, you can actually see that C is not connected to anything. That's now at an infinite impedance. And so we really just have the sum of Z sub A and Z sub P, Z sub A with Z sub B in parallel with Z sub C across terminals A and B as far as its impedance. Let's write that down before we forget it. What I just said was the delta configuration for the impedance seen between terminals A and B was this product of Z sub C with the sum of Z sub A and Z sub B. That's the numerator. So we're really looking at this parallel combination of Z sub C with the sum of Z sub A and Z sub B. And as we know, when we perform that parallel combination, we just have the sum of impedances in the denominator. Now, if we want these configurations to be the same, we want that impedance between terminals A and B to be equivalent to the impedance we see between terminals A and B in the Y configuration. In this case, virtually erase the black impedances and look at what you have as far as an impedance between terminal A and terminal B with the blue impedances. Now we have Z sub 3 not connected to anything, it's off in space. That presents an infinite impedance, and for that reason the only impedance between terminal A and B is the sum of Z1 and Z sub 2. And that we want to be equal to the impedance that we have between terminals A and B for the black impedances, or the delta configuration. And there, if you virtually erase the blue impedances, now you can see that Z sub C is in parallel with the sum of Z sub A and Z sub B. And that's what we've written down here. If we do the same thing between B and C, we actually see, or will observe, that Z sub A is now in parallel with the sum of Z sub B and Z sub C. And the terminal in the Y configuration, I'm sorry, the impedance in the Y configuration between B and C is just the sum of Z sub 2 and Z sub 3. Finally, if we look at C to A, now we have Z sub B in parallel with Z sub A plus Z sub C in the delta configuration. Which produces this formula. And that's now equal to, between terminals C and A, that's now equal to Z1 plus Z sub 3. What we want to do now is, if we are going from delta to Y, we want to find a formula, let's say for Z sub 1, in terms of the ABC, or the delta impedances, using these three relationships. We now have three equations in these six unknowns, and now we want to solve for one of those unknowns, this Z sub 1, in terms of the other three delta impedances, Z sub A, B, and C. What we're doing then is we're wanting to solve, or we're solving for Z sub 1, and that's actually the Y impedance that's touching terminal A in the schematic diagram. And we want to now find Z sub 1, or solve for Z sub 1, in this set of three equations. In order to do that, we're going to actually combine these equations in a special way, and the special way you can sort of infer from looking at the right-hand side. If we take the first equation, the AB terminal equation, and we subtract the BC equation, we end up getting rid of the Z sub 2. And then if we look at the third row, the CA expression, and if we now add back in Z sub 3, we'll get rid of Z sub 3, and we'll end up with only 2 Z sub 1 on the right-hand side. And that's then going to be easily solvable for Z sub 1. That's what I'm meaning by combine the above equations in the following manner. We want to take the equality, or equation AB for the AB terminals, take from that or subtract from that the formula for impedance equivalences between terminals B and C, and add back the equivalent impedances between C and A. If we do that, then I hope we will see that here I have Z sub C times ZA plus Z sub B minus Z sub A times ZB plus Z sub C plus Z sub B times Z sub A plus Z sub C. That's coming from the black equations or the delta equations. Let me write that down. We now have Z sub C times ZA plus ZB, that's the AB numerator, minus Z sub A times Z sub B plus Z sub C, plus Z sub B, Z sub A plus Z sub C, and all of those denominators were the same, and they were just the sum of the three delta impedances. That's now equal to, if we look at the right-hand side, we're taking Z1 plus Z2, subtracting Z2 plus Z3, and adding back Z1 plus Z sub 3. So we're taking Z1 plus Z sub 2, subtracting Z sub 2 plus Z sub 3, and adding back Z sub 1 plus Z sub 3. Now, if we multiply that numerator out on the left-hand side or in the black equation, we will get a pairwise combination of a lot of different impedances. And I will maybe try to, when I multiply these out, keep the alphabetically first coefficient in front. So Z sub C, Z sub A becomes ZA, ZC plus ZB, ZC minus ZA, ZB minus ZA, ZC plus ZA, ZB plus ZB, ZC. And all of that is still over the sum of those three impedances. And that's now equal to Z1 plus Z2 minus Z2 minus Z3 plus Z1 plus Z3. If we look at what we have up above, the AC, we have that with a minus. We'll lose that combination. We have a Z sub B and a Z sub C twice with a positive sign. I'll leave that, but we have a minus Z sub AB and a plus Z sub AB. And if we now write down what is left, we have 2 Z sub B, Z sub C over ZA plus ZB plus ZC equaling, and now the blue on the right-hand side, we can, I hope, see that we lose those two. We lose those two terms, and we're only left then with 2 Z sub 1. These 2's cancel, and now we have our relationship that we were looking for. We can now write down that Z sub 1 is in fact Z sub B, Z sub C over Z sub A plus Z sub B plus Z sub C. And that's, in fact, in the textbook, that's equation 51 in Chapter 9. We could do a similar analysis for Z sub 2 and Z sub 3. I'm not going to go through that, but I think you can see how that could be done. And we end up then with Z sub 2. Now if we go back here, Z sub 2, what's touching it is Z sub C and Z sub A, and then we'll just form that product and divide by the sum of ZA, ZB, and Z sub C. I had the pairwise product of C and A's impedance because those two touch terminal B. Then I have ZA plus Z sub B plus Z sub C, and the Y impedance Z sub 2 likewise touches terminal B, and this is equation 52. If we do the same observation with the Z sub 3, we now see that Z sub 3 is touching the C terminal, and the impedances touching that terminal in the delta configuration are Z sub A and Z sub B. We form their product and then divide by the sum of those three delta impedances. And that then gives us the three equations that we need in an unbalanced impedance configuration to take us from a delta, those are the A, B, and C, to a Y impedance interconnection. So I will call that then the Delta-to-Wye transformations. If we want to now go in the other direction, if we were starting with a Y connected set of impedances, back to the delta, it's now helpful to realize that we already have this delta to Y relationship, and we can use that to help us go from Y to delta, or to derive the equations that allow us to go from Y configurations of unbalanced impedances to a delta configuration. So to go from Y to delta, we can do a little more analysis. And what we're going to do, we're going to get a little creative here, but now let's multiply those three equations that we just derived, the above equations, equation 51, 52, and 53 in Chapter 9, and the way that we are creatively going to multiply those is we're going to multiply those together pairwise. Meaning, if we take Z sub 1 and multiply it by Z sub 2, we end up with a square of the sum of ZA, B, and C in the denominator, and upstairs we have Z sub C twice, or squared, and Z sub A and Z sub B. Let me write that down. So if we pairwise product the expression for Z1 and Z2, we end up with Z sub C squared times Z sub B, Z sub A, and the denominators each had this sum of impedances, and since they each did, then that becomes squared. Now I'm going to need these formulas in a bit, so I'm going to label them. I'm going to label that equation alpha. Then I will create the next equation, beta, by taking the pairwise product of Z sub 2 and Z sub 3. I won't scroll back, but that becomes Z sub A times Z sub B, Z sub C. The denominator is going to be the same as the previous product. That's now my beta equation. And my gamma equation is now going to be Z sub 3 times Z sub 1, which is now Z sub B squared, Z sub A, Z sub C, all over the same denominator. Now that I have that collection of equations, another set of three equations that contain the Y impedances and the delta impedances, let me now add those together. Let me add alpha, beta, and gamma. On the left, it's not going to be that complicated. It's now Z1, Z2 plus Z2, Z3 plus Z sub 3, Z sub 1. On the right, it's a little bit more involved. I'll give myself some space, but now I have a Z sub A squared ZB ZC. I have a Z sub B squared ZA ZC, and I have a Z sub C squared ZB A B Z ZB ZA. What did I just say? I had a Z sub A squared times Z sub B Z sub C plus a Z sub B squared Z sub A Z sub C plus a Z sub C squared Z sub A Z sub B, all over the sum of those three impedances squared. To see something that I might be able to factor out of that numerator on the right-hand side, virtually get rid of that square by multiplying it out. So now I have Z sub A times Z sub A, Z sub B, Z sub C. I have Z sub A, Z sub B, Z sub B, Z sub C. And I have Z sub A, Z sub B, Z sub C, Z sub C. You can see that I have a common term in the numerator of all of those, of the product of those three impedances, ZA, ZB, ZC. Then if I look at what's left over after factoring that common factor out of all three, I now have the sum of those impedances. That looks nice. Now that I can use that to eliminate one of those factors in the numerator and denominator, so that now this pairwise sum of 1, 2, and 3 becomes equal to Z sub A, Z sub B, Z sub C over the sum of those three impedances. Now, what I'm wanting to do is I'm trying to go from Y to delta, and the Y's were the 1, 2, 3s, the deltas were the ABCs. Can I obtain a formula for just Z sub A? If I go back and look at my equation for, well, let me look at this one. I have ZA, ZB, ZC. I need to get rid of ZB and ZC. If I go back here, and if I look at a ZB, ZC, that's my Z1 equation, which means that if I take what I have so far, this pairwise sum equaling the right-hand side, and divide both sides by Z sub 1, I will actually isolate Z sub A. Let me write that down. To solve for the delta impedance Z sub A, we need to divide out Z sub B, Z sub C in the numerator of that expression. But if we go back to our earlierly derived relationships, we can see that Z sub B, Z sub C is in the numerator, in the Z1 equation. And that was equation 51, or 951. If we now divide both sides of this, there's the right-hand side and here's the left-hand side. Let's now divide both sides by Z1. We have the pairwise or the sum of the pairwise products. We're going to divide that by Z1, and that's going to equal now ZA, ZB, ZC all over ZA plus ZB plus Z sub C. That was the right-hand side. What we now want to do is divide by Z1, but now the Z1 that we're going to use is this Z1 expression, which is ZBZC over the sum of those impedances. So now we're going to divide by ZBZC over ZA plus ZB plus Z sub C. If you didn't see me scrolling and just looking at these notes, you're going, where did that come from? Well, that was just our formula for Z sub 1. Now, with that, we can see that the BC product can be divided out. The denominator can be divided out. And now I have a formula just containing Z sub A. Therefore, the delta impedance Z sub A is now simply this sum of pairwise products of the Y impedances divided by Z1. That's equation 54 in chapter 9. And similarly, then, we can derive the other two relationships. The B impedance, which is now Z sub B, and in this case, we just know that we're always going to have in the numerator this sum of pairwise products. And in the denominator, if we look at what Z sub B is in our picture or in our schematic, it's now opposite Z sub 2, and that's the impedance in the Y configuration that we need to divide into this pairwise sum of products. And that's now equation 55. And finally then Z sub C, the numerator is again this sum of pairwise products. We'll divide that by the impedance that's opposite the C terminal, or that actually is touching the C terminal, which is Z sub 3. And that's now equation 56. These three equations are now how we would go from Y to delta in unbalanced impedances. As we demonstrated in the very first, when we were talking about our second goal, for the balanced configuration, those 6 relationships default to something quite trivial. In this case, we are going to let the delta impedances just be labeled as Z sub delta, and those were our ABC impedances. And we are going to let our Y impedances be labeled as Z sub Y. If we now go back and just say, well, let's look at what this means if we apply that balanced set of impedances to equation 951, that said that we had Z sub 1, which in our case is now just going to be called Z sub Y. That was equal to Z sub B and Z sub C product, but those are just Z sub deltas, and then we had the sum of those 3 Z deltas. So now we have Z sub delta over this sum of 3 Z sub deltas. can divide out one of those z deltas from both numerator and denominator, and we end up with then zy actually being a factor of 3 less than the z deltas. Or if we multiply the 3 on both, or multiply by 3 on both sides, we find that the balanced relationship now is that this delta impedance in the 3 places in the delta interconnected structure is 3 times the impedances in the Y configuration. And that's what you would then use when you are converting between Ys and deltas and Ys in a balanced load problem.